Here we are, the layout for a concrete production process. You can see on the left the raw material arrival, and on the right 3 different machines. This raw material can be processed indistinctly by one of these 3 machines, so you can process the raw material by machine number 1, machine number 2, or machine number 3. And you can see that the Manhattan distance is different for every machine. For machine number 2, the Manhattan distance from the raw material section to the machine is only 1. Manhattan distance equals to 1 distance unit. I don't know if it's meters, if it's whatever. And then on the other hand, you have 1, 2, 3, and 4. That's the Manhattan distance for machine number 1. And for machine number 3, the Manhattan distance is 1, 2, and 3. That's the distance that the raw material must run in order to be processed. So the most energy-saving choice, as you can see in the figure, is to process the raw material always on machine number 2. Why? Because the Manhattan distance being run by the raw material is the smallest. But we want to assign a batch of 9 orders, can you see here, from order number 1 to order number 9, and all of them can be manufactured on any machine, 1, 2, or 3. But as you can see here on this table, the process times for every machine are so different one from the others. Here, machine number 1 has a process time of 10 time units, while machine number 2 a process time of 50 time units, and then machine number 3 20 time units. So machine number 2, that it has the smallest Manhattan distance, this machine spends a lot of time doing the whole process. So our interest is to minimize, that's the key word of this problem, minimize the sum of all the distances run by raw material weighted by the process time. So it's like a compromise between the distance run by raw materials and the process time these raw materials will spend in every machine. Well, in the machine where they are being processed. But we have several constraints. Each order will be assigned to a single machine, so each order single machine in M1, 2, or 3. And we don't want empty machines, okay? No empty machine is wanted unless one order should be processed on any machine. And no machine should manufacture more than half the orders in a single batch. We have 9 orders, can you see here, 9 orders in this single batch. If we divide by 2, this way we have the half the orders, then this is 4.5, so no more than half the orders means that every machine should manufacture a maximum of 4 orders. So with all these preliminaries, we will define the optimization array first. As you can see here, the optimization array has 27 elements. And every element, as you can see here, can have a value of 0 or 1. At the beginning we don't know, as you remember, we don't know the value for every element within the optimization array X. That's our objective, to find the values of all these elements in X. But we know that we are dealing with binary optimization problems. So this binary means that every variable within the optimization array can be false or true, 0 or 1. And what's the meaning of every X within this optimization array? Let's have a look first here at X1. X1 means order number 1 processed in machine number 1. We don't know if this x1 will be false or true at the end of the problem. But now we must define a variable that means if order number 1 will be processed in machine number 1. So if we proceed according to this sentence, x2 is order 1 being processed in machine number 2. x3 order 1 in machine number 3. So we have 9 orders, 3 machines. So that's how I have defined the meanings of all these elements in X. So according to this, X25 means order number 9 processed in machine number 1, 2, or 3 for X26 and X27. Then what's the objective function according to this optimization array definition? The cost function, remember, it's the distances weighted by the process time. So we will multiply every process time by the Manhattan distance. So everything that deals with machine number 1 will have a coefficient in the cost function that will be 10 multiplied by 1, 2, 3, and 4. That is the Manhattan distance for machine number 1. So here we have the Manhattan distance, 4. Here we have the process time, okay? And the first element in C, you remember that the cost function f will be C, an array of coefficients, multiplied by the optimization array. This is a column array, as you can see here. And this is a row array. So what's C? First of all, is how x1 contributes to the optimal solution. And x1 contributes to the optimum solution according to this. x1 means order 1 in machine 1. So machine 1 has a process time of 10, so that's 10, multiplied by its Manhattan distance, 4. What's the second element in C? The second element deals with x2 because it's the coefficient that will be multiplied by x2. This x2 means order 1 in machine number 2. Machine number 2 has a process time of 50. So now it's not a 10, but it's a 50. Multiplied by what? Multiplied by 1, because 1 is the Manhattan distance of machine number 2. And the same goes for C3. C3 deals with x3, as you can see here, and x3 means order 1 being processed in machine number 3. Machine number 3 has a process time of 20, so 20 here, multiplied by what? 1, 2, and 3, because 3 is the Manhattan distance for machine number 3. What about C4? This is the fourth element. C4 is the coefficient that multiplies x4, and x4 means order 2 in machine number 1. Order 2 in machine number 1. Let's have a look at machine number 1. It has a process time of 10 and the Manhattan distance for machine number 1, it's again 4. And as you can see here, we have these 3 elements that will be repeated one time and another, and we will have 9 times this 3 element array. So we will have these 3 elements 9 times in order to define all the coefficients within the array C. in the cost function, in the objective function. That's how I have done it in MATLAB environment. You can stop the video and have a look at this. You have the files in the virtual campus, okay? But the key point is that this cost function is like a repetition of these three elements 9 times. So at the end, we have no best solution for every order. At the end, the important thing is that it only depends on where is the machine placed according to the raw material reception and how long it takes to process the raw material for every machine. Only these two elements, and these two elements, they have nothing to do with the order number. So that's why we have we have to repeat this 3-element array 9 times. So all the others remain equal. Let's have a look at the constraints. First of all, no empty machine is wanted, and then no machine should manufacture more than 4, you remember? So every machine must manufacture between 1 and 4 orders. Yeah, because half the orders in this batch is 4.5. So a minimum of 1 order, a maximum of 4. So let's have a look at machine number 1. Machine number 1 can have all these possibilities. Have a look at this. This X1 is order number 1 in machine number 1. I don't know if this will be true or false, but I must define the constraint within the problem environment. What is X4? X4 is order 2 in machine number 1. What is X7? X7 is order 3 in machine number 1. This is order 4 in machine number 1, 5, 6, 7, 8, and 9. This is order number 9 in machine number 1. So for all these elements within the optimization array, I want all of them to be, or the addition of all of them to be greater or equal than 1, because I don't want this machine empty, and the addition of all these elements must be smaller or equal than 4. Why? Because a maximum of 4 orders must be processed by machine number 1. The same goes for machine number 2 and machine number 3. As you can see here, we have all the indices are moved only one position. Can you see here? One position. And the important thing is that we have like a lower bound and an upper bound of all these elements added together. So, for example, order number 1, order number 2, 3, and 4 could be processed by machine number 1, okay? But no more than 4 orders, and no less than 1 order. So all of them, the addition of all of them must be greater than 1 or smaller than 4. Maybe we have a single 1 in all these positions. Maybe I have 2 1s in these positions. Maybe I have 3 1s, but no more than 4 1s in all these positions, because all these positions belong to machine number 1, and all these positions belong to machine number 2, and this for 3. But MATLAB only understands this kind of inequalities, smaller or equal than. So first of all, we have no problems with this, because you can write x1 plus x4 plus x7 plus etc. smaller or equal than 4. Here we have no problem. But the first set of constraints has split it into two different set of constraints. First of all, the smaller or equal than, and then we have the greater or equal than. These inequalities must be rearranged, rewritten in this form. All the elements must be put in a negative form. Can you see here? In a negative form. Can you see the 1? Here we have a plus 1, a positive 1, yeah? But here it has been turned into a negative 1, and all these coefficients are 1, positive ones, and here all these coefficients are negative. They have turned into negative. Yeah? In order to what? In order to change the direction of the inequality. So now you have all this first set, all these inequalities in the first set splitted into two different inequalities, but both are smaller or equal than something. So this is how I have translated into a MATLAB code. Can you see here the negative and the negative at the bottom? So we have two different sets, A1, B1. Can you see the 4 in here? For the first set, here we have A1 multiplied by x, smaller or equal than B1, and here I have A2 multiplied by x, smaller or equal than B2. These are the negative ones. So let's go now for the final, the last type of constraints. Here we have equality constraints. And these equality constraints, they deal with that all the orders must be assigned to a single machine. So what about order number 1? This is order number 1 in machine number 1. This is order number 1 in machine number 2. And this is order number 1 in machine number 3. So one out of these three possibilities must be equal to 1. So this way, order number 1 will be assigned maybe on machine 1, maybe on machine 2, or maybe on machine 3. But it will be assigned for sure. So the same goes for order 2, 3, 4, 5 until 9. Okay? And this is the SPI, you know, in MATLAB, SPI A equality 1. If we SPI this, we have, as you can see, the first three positions of the optimization array. The first three positions, 1, 2, and 3, are the indices of these positions, must be equal to 1. Equal to 1, as you can see here. Equal to 1. This is SPI of B equality 1. So finally, I must do the constraint compilation. Here you have the inequality constraints. You remember, we have two different sets of inequality constraints. Yeah, this means this A1, B1, you remember, smaller or equal than 4, while these are the smaller or equal than minus 1, you remember, for the lower bound and the upper bound of orders for every machine. But we have a single set of equality constraints, as you have seen before, in order to assign every order to a single machine. And finally, we call the int limprog, you remember, for the MATLAB environment, This is the coefficients of the cos function. This will be c. You remember all the coefficients for the cos function. This means that from x1 till x27, all of them are integer variables, integer linear programming. So all of them, all of the elements of the optimization array are integers. This A and B, as you can see here, are the inequality constraints. These are the equality constraints. And finally, here we have the lower bounds. You remember that all the elements in X can have two different values, 0 or 1, yeah, false or true. So the lower bound is 0, while the upper bound is 1. Both are integers, but additionally they are binary. A possible solution is this. Can you see machine number 1? Yeah, machine number 1 will have orders number 1, 2, 3, and 9. Can you see that here there are 4 orders? On machine number 2 we have 1, 2, 3, and 4 orders, and on machine number 3 there are 6 orders. If you remember, we have the Manhattan distances. They were 4, 1, and 3 for the machines. Then we have the process times. For machine number 1 was 10, for machine number 2 50, and for machine number 3 was 30. As you can see, if you do the product, this is 40, this is 50, but this is 90. So the algorithm tries to assign the minimum number of orders to machine number 3, because their contribution is the contribution to the cos function is the greatest value, and the objective was, remember, to minimize. So this is not contributing to the minimization of the cos function. So that's why here we have a single order. That's the minimum as possible.